All right. Hello, class. Sorry, but today we're going to be talking about trig identities. So, just as a reminder, or perhaps for the first time, an identity is it's an equation that is always true. It doesn't matter what you say. I mean, it's best seen by some examples. So, one second. I'll put it in green because it's good. So, for example, identities are equations that are always true. It's kind of hard to see that. It's a little better. Okay. Bear with me. Bear with me. Identities. So these are equations that are always true. And there's some low-hanging fruit. There's like 5 equals 5. There's x plus x is always equal to 2x. Maybe things like x squared is greater than or equal to 0. This is a little trickier because it's not an equality. It's an inequality, but it's still true, always true for any x. We also have, like on the opposite side of identities, there's contradictions. So these are equations that are never true. This is things like 5 equals 7, or x squared equals -1. You may be laughing at that one, because sometimes that's true, but for our purposes, no. Can't have something that squares to a negative number that's related to this. And then, like, in between, you've got your conditionals. And these are things that are sometimes true. Things like x plus x equals x. There's some values of x that make this true. For example, if x is 0, but otherwise it's not true. So sometimes it works, sometimes it doesn't. Things like cosine of x equals 1/2. There's some x values where that's true, where we rotate and we're a half radius length away from the center, but not all x values. These are always true. And so we're going to be looking at some identities today, things that are always true, regardless of what x is or the variable is, anything like that. So we actually saw one back when we were working in 8.1. So if we're working on a circle, let's say we've swept out some angle theta, then we have some triangle here, right? This is, so if this is some point x, y, and I'm going to assume that my circle has radius 1, just to simplify things. So this length is x, this length is y. By virtue of this being a triangle, a right triangle, and the hypotenuse of this triangle is the radius of the circle, so it's 1, we get that x squared plus y squared equals 1. And this is just the Pythagorean theorem, but it didn't matter where this triangle was situated. Even if theta is lying on the vertical, if it's at pi over 2, then my x and y pair are just 0 1, my x is 0 and my y is 1 because I'm at the complete top. And so then 0 squared plus 1 squared does indeed equals 1. So it's true for any triangle, any theta that you put in. And so we actually have x and y in terms of trig, in terms of our trig functions. X is the horizontal distance to the right of the center, y is the vertical distance above the center. And as we saw, that means x is cosine of theta, and y is sine of theta. So cosine theta squared plus sine theta squared is equal to 1. This is true for all values of theta. Any theta that you sweep out in this circle, if you take the cosine and square it, and you add it to the sine that's squared, you'll always just get 1. So this is an example of an identity. Always, always true. And so, by virtue of it being an identity, we can maneuver it around. We can go back and forth. Let's say I just wanted to get one of these on its own. It's also true that cosine, and here's just a notation thing. Sometimes we write the square immediately after the letters cos. So we'd write something like cos squared, and then put theta, but these mean the same thing. I personally like this. If I'm doing a lecture, I'll do this every time, because I think it's more obvious. You take cosine theta and you multiply it by cosine theta. This is a little more ambiguous, so I'm going to try and avoid this, but just be aware, you will see it written like this sometimes. But cosine squared theta, I can rearrange this equation. So if I just subtract the sine theta squared, I'll get 1 minus sine squared theta. This is also true. This is the same identity. I've just done some algebra to it. And so this is, a big one that you'll always be working with. Something to be aware of. Really, a lot of the trig identities that we'll use are built from this one right here. And yeah, so let's take a look at the investigation. So today we were going to be doing 8.3 problems number 2 and 3. And so some of these problems without guidance can be a little tricky. And so let's just look at the first one together. So problem 2, part A, states, so we want to rewrite these expressions to generate an identity. And so we have, let's see, sine of x over cosecant x plus cosine x over secant x. And so we just want to rewrite this into something a little more familiar. Right now, this is a little unwieldy, it looks scary, but we can only do what we have to work with. We only have this small toolbox, and so really all I'm going to do is just start rewriting things in terms of what I know. And what I mean by that is I don't like these inverse trig functions, cosecant and secant. I'm just going to replace them with what I know they are. So as a reminder, cosecant is going to be 1 over sine. Sine and cosecant are related, cosine and secant are related. So this is the same thing as sine of x over cosecant, but cosecant is 1 over sine of x. and on the right I have cosine x over secant, and secant is 1 over cosine of x. And so now I'm just going to simplify this further because I have a fraction, this is like sine of x over 1, divided by 1 over sine of x. Really, when I'm dividing by a fraction, so think of this whole thing as just fractions in the denominator. When I'm dividing by a fraction, I multiply by the reciprocal. So this becomes sine of x, that's what I have on top, and I multiply by the reciprocal. So the reciprocal of 1 over sine is just sine. So I get sine of x times sine of x. And for this term, I multiply by the reciprocal, so I multiply by cosine x over 1, or just cosine x, and I get cosine x times cosine x. And here's what we mean. This is just something times itself plus something times itself. So I'm just going to rewrite it as sine of x all squared plus cosine of x all squared. And now we're back to our familiar identity, sine x squared plus cosine x squared. This equals 1. So this thing that we started with is really our classic Pythagorean identity in disguise. And it also wants us to, make sure we state the values of x that create undefined expression values. So I said that this is true for all x, but here, what I'm doing is it's basically the same thing, but I have to worry because there is division going on in this original statement, this expression. So I have to worry about when is this 0 and when is this 0. When is cosecant 0, when is secant 0. Now, the good news is cosecant, which is 1 over sine is never 0. As a reminder, a fraction is 0, so something over something is 0 only when the numerator is 0. So because 1 is never 0, 1 over sine of x will never be 0. So I don't have to exclude any x values for this one. Okay, so this is kind of just the strategy for what we want to do for this one. Let's do one more, just so we have the right idea. So let's look at I'll let you guys do B. Let's look at C real quick. So C says